Thanks for the introduction. So yeah, we're going to be talking about this paper, and I'm James Cagalawan. So this paper was written by Zhu, Mutagi, Lim, Gupta, Lee, and Farhadi. I'm just presenting it. They work at Stanford, Allen Institute for AI, Carnegie Mellon, and the UW in the US. So what is navigation? We've seen navigation before. This is like the classic reinforcement learning problem where we're trying to navigate a sort of scene in a grid world. We're trying to have the agent, the robot, reach for the jewel while avoiding sudden death by falling into the fire. And the way that we can solve this is we assign numeric rewards to these grid cells. So say you get +1 reward for the jewel and a -100 reward for the fire. And then we can just use any reinforcement learning algorithm, say Q-learning, to learn a policy that will bring us to the jewel. So some applications of this, just to motivate it a bit more. So I guess this sort of example would be a treasure hunting example where you have a robot trying to find a jewel, sort of like as if they were Tomb Raider or Indiana Jones or something, they don't want to fall in the fire. And it's the World Cup right now, so I guess another application would be trying to get to a soccer ball as a robot while trying to avoid the other opponent, not ram into them. Drone delivery of pizzas to like lecture halls, avoiding geese from stealing your pizza. Visual or self-driving cars, driving to your house and not running over any geese. A more serious example would be search and rescue robots looking for people in a forest. Like say a child were lost, how can we use a drone to find this child? And the application we're going to be focusing on today is domestic robots. So say you have a robot and you want it to do chores for you or just like check up on the fridge, see if you're stocked or if your stove is on while you're away. The problem formulation we'll be looking at is there's going to be multiple locations in our house that we want to navigate to. We won't be looking at sort of pitfalls like fires or anything that it'll avoid. And the actions that a robot can take are moving forward or backward or turning left and right. So this comes with multiple problems. So navigating to multiple targets. We saw how to navigate to a single target with Q-learning, but that might pose a challenge if we try to use the same method for multiple targets. The second problem is on a real robot, we usually have sensors, and those are high dimensional, and it can be challenging and time-consuming to train. And the third problem is that training on a real robot can be very expensive, like time-wise, safety-wise, and all that. So we want to make training as fast as we can. So if we have this maze, what happens if we try to apply our sort of standard reinforcement learning technique on it, where we just assign a reward to a grid cell and learn a policy that way? So anyone see a problem with what happens if we just assign a +1 to all of these targets you want to reach? Yeah?
It'll just hit on the closest one?
Yeah, basically. It'll reach a target, but we can't specify which target we want to reach. So it's going to be highly dependent on where this robot starts off in this grid world environment. So this technique clearly won't work. Another idea that we're going to explore a bit more is training a different policy for every target. This will definitely work. Like if you want to go to the bed, we just use the bed policy. If we want to go to the TV, we use the TV policy. But there's going to be some scaling issues here because we will have one policy per target. And that becomes a problem, especially when we have an image, as we'll see here. So now we're in a 3D environment, and we have a target image we want to reach now. And doing that same idea of training a single policy for every target image clearly won't scale because we have these high-dimensional images. So we're going to be looking at how to deal with that. The sort of traditional methods in robotics are to decompose the problem using into different sort of pieces, and then use the solutions from each subproblem into the next one until we have our actions. This is one of the standard sort of pipelines that is proposed in Autonomous Mobile Robots, the standard textbook in the area by Roland Siegwart and Illa Norbeck. So let's walk through the pipeline. So here we have the input image of the robot. So it sees this sort of bed, closet, and this just bedroom. And we're trying to reach this this part of the closet, so the right part of the closet as our target image. And we want to drive the robot to there with a set of actions. So we have this image. We can run some perception algorithm on it. And that typically involves some sort of localization and mapping. So you have the robot, and it builds a map. And here, the map representation we have is an overhead bird's eye view of the world. And another part of perception is detecting objects in the world, such as like the bed, the computers, the shirt, the pants. So now we have the objects, we have a map, we have the robot's location in the map. Another task we have to do is world modeling. So we now decompose the environment into a sort of representation that is suitable for planning. We've seen the grid before, so we're just going to go with that. So we grid up the world into occupied and free spaces. And then we take that world model, and now we can plan on it. So we have that image, and we sort of identify which grid cell we want to reach from that image. And then with that grid cell and our start position, we can then just run a shortest path algorithm to drive us to that location. And from that path, we then have a set of actions that brings us to the desired location. So that works extremely well. Like, it solves the problem. But the problem we have here, or I guess an improvement area we have, is that each of these subproblems has their own sort of specialized algorithms to solve them. And it would be nice if you could just have this entire pipeline for robotics replaced with a single algorithm. And since this is a reinforcement learning class, of course, we're going to use a reinforcement learning algorithm. So we want to have a deep reinforcement learning architecture that handles this visual navigation problem that just takes in the raw pixels and produces these actions. And we also want to have it work on a real robot. The main challenge of reinforcement learning in robotics is data efficiency. If you think about how if you just start off a neural network with random weights and run that policy on the robot, it's probably going to break itself before it learns anything like useful. So data efficiency is very, very important. And another idea we can use to get around this is to initialize the policy from one trained in simulation and then fine-tune that on the real robot. So that's what we're going to be doing, and that's what the authors propose, and their method handles that well. So our overall goal is to solve that visual navigation problem, but with a method that has high data efficiency. So one that requires fewer samples, fewer episodes for us to train a reasonable algorithm that reaches the targets in the environment. All right. So the overview of this architecture. So we're going to have our observations and our targets input into the network. And instead of having a separate policy for each target, we would now embed the target into a feature space, this 512-dimensional space. And we do that using the ResNet50 model, which is a standard deep learning model that has been trained on ImageNet, which is a data set for image recognition and classification. This is a Siamese network. So we have our observation also going through this ResNet50. And their weights are shared between these two, and they're not trained at all during reinforcement learning. We just use these ResNet50 units to generate these feature vectors. So now we have a embedding of our images into the space. And what that lets us do is, instead of having a different policy for every sort of viewpoint of that target, so imagine if the robot were slightly tilted, instead of training a different policy, the policy between this image and one that is slightly perturbed in rotation or translation should be pretty much like identical. It shouldn't be too far off. So that lets us leverage different, the geometry of the of the scene in our training our algorithm. And then we then use these embeddings. So we have two 512 dimensional vectors from the observation and target, and we fuse them together into another layer. And then we then have another layer. And this produces a policy and a value. So this is similar to the actor-critic methods we saw in class. But instead of training a different target on each, or training the same target in each thread as what you would do with the actor-critic, where if you were just running a maze, then you'd be training the same target, then you'd instead be training different targets in the environment on different threads. So with that, we'll now look at what our simulation environment gives us. So they call this simulation environment the House of Interactions, or Thor. It's called AI2 Thor because it was made by AI2, the Allen Institute for Artificial Intelligence. So what this environment has is it lets you, sort of like a video game, you can jump around in 3D and move. And they have 32 scenes of household environments. And they can, the reason they made this simulation environment is because they wanted high fidelity compared to other simulators. So if you want to do transfer learning, then it's important that your simulation and your real-world setup are pretty similar, or else there might be more learning to do. And we want to avoid learning on the robot as much as possible because of the cost associated with that. So we now have these different scenes. The authors also give a different architecture. They slightly tweak it. So because we have multiple scenes, instead of having a single fully connected layer after the embedding fusion and then output policy and value, we can train these scene-specific layers on different scenes themselves. And we're going to look at how that affects the results in the experiment section. Just as another tweak they did is instead of using the simulator's full capabilities of continuous motion, they discretized the world into sort of grid. So they can only move forward at half a meter and turn 90 degrees with no uncertainty in there. So just to make training simpler, they also compare this against what would happen if they didn't do this and they trained using continuous actions with noise. And we're going to see the effects of that coming up. So now for the experiments they performed. So they compared it against different methods. So there's heuristic methods, purpose-built RL methods. So purpose-built just means single target, and a target-driven RL, so one that considers a target. So the heuristics are a random walk. So just the robot just like moves around the environment in a random way. And so they compared the average trajectory length across different scenes and across different targets using these different methods. So if you just did a random walk, your average trajectory length would be 2,744, which is really high. But then if you used the shortest path algorithm, which is essentially the best you could do, then you have a trajectory length of 17.6. Comparing it to other RL algorithms, they compared it against one-step queue, which is a deep queue network, and the actor-critic methods across one thread or 4 threads. And the single branch method is the one with a scene-specific layer, or with a single scene layer shared across scenes. And the final method that they call it is the one with the scene-specific layers. So you can see that deep queue networks don't really perform as there's very little improvement compared to a random walk. Actor-critic methods do a bit better, but their method does really well compared to these other methods that use reinforcement learning. So you can see their trajectory length is 210.7, and the best non-target-driven RL method they tried against was only 723. So they effectively cut the average trajectory length by a third using their method. So another experiment they did was they wanted to evaluate how data efficient their model is. Because again, robotics, it's very hard to train on a real robot, and we want high data efficiency. So we now have these different, the different methods compared by training frames. We're comparing the average trajectory length over the training frames. And we can see that the target-driven final method learns a lot faster. So its average trajectory length decreases a lot faster compared to other methods over the number of training frames. So it's a lot more data efficient than deep queue networks and actor-critic methods. which is a real plus in this sort of application space. To evaluate their navigation results, here's a really cool result they have. So on the left here, we have a bird's eye view of the environment. And on the right, they performed a TSNE visualization of that middle embedding vector, if you remember from neural network architecture. So what this TSNE does is it sort of clusters that high-dimensional 512D vector, and it projects it down into 2D. And if you look at the bird's eye view and look at the dots, the green dot, the red dot, the yellow dot, and the orange dot, and you look at the position of the sort of equivalent dots of the images in the TSNE embedding, we have a similar sort of layout spatially. So we have the green dot most left, and the yellow dot most right, and this orange dot here in the bottom, and the red dot just in between. So without any implicit or without any explicit feature engineering to make a map, the reinforcement learning algorithm itself seems to have learned an implicit map of the environment and has and a way to localize itself against the map just from the raw pixels using this neural network architecture, which I think is a really cool visualization for them to do and a really cool result because maps are often thought of as unnecessary for reinforcement learning, like these sorts of end-to-end methods, but it's nice to see that the map here is just being learned implicitly. So that's it for navigation. We're going to be moving on to how this method generalizes across scenes and across targets. So first we're going to look at how it generalizes across targets. So what generalization across targets means is if I train on a certain set of targets, and then I look at how it works on new targets, how will my algorithm work? So they introduce a new metric here called the new target success rate. And what that is how successful the algorithm reaches the target in less than a threshold, which I believe was 500. So they looked at how it would work if they trained on more targets, how that success rate improves, and by varying the distance from the target they're trying to reach as well. So if you start off like right beside your target, so the blue bars on each one, then you'll have a very high chance of just reaching the target because you just need to take one step. But if you're very far off, then you have a lower chance of reaching it. So we can see here that as they trained on more targets, the success rate of their algorithm worked out a lot better. So you can see this sort of climb between each of the bars, reaching each color. So the blue one goes up, the red one goes up, the yellow one goes up, and the green one goes up. So what this is telling us is that by training on more targets, the algorithm is better able to generalize to new unseen targets. So like if the algorithm can reach the fridge, can reach the bed, then and it hasn't ever went to like the couch, then by training on more targets rather than just a single target, the algorithm can, this architecture works better if you train on more. And we'll now look at how it generalizes to new scenes. So a new scene is like a new environment. So like if you were like running this in the kitchen, how it would work if you had run it in the bedroom. So here we're evaluating the average trajectory length over the training frames. And so as you train on more scenes, so here we have the blue as the fewest scenes and the purple as the most scenes, being if you train on 16. The average trajectory length goes down a lot faster using this by training on more scenes rather than fewer. And they also evaluated how well their scene-specific layers did compared to having a common scene layers. So if you just have a single scene layer shared across all of the scenes, then this is about how well it would do by the end of the training algorithm. So it's not very good. But if you fine-tune in the end, then it still does pretty well. It does better than just one scene, but it clearly is outmatched by training on more scenes with scene-specific layers. So Now we'll look at some experiments using continuous space. So by what continuous space means is that instead of always having half-meter steps and 90-degree turns, there's now noise as well as collisions with the environment. So if the robot hits something, it might just stop or it might push that object away. So they trained it using this sort of environment as well. They saw the same actions, move forward, move backwards, turn left, turn right, but now there's a bit of noise injected into there, as well as the possibility of collisions. And what ended up happening is that it still was able to learn how to reach targets, but it just took a lot longer for it to learn that. So it was about 50 million more training frames just to train on a single target compared to their discretization of the world into a grid. And using this, they could reach the door in an environment using 15 steps, while a random agent took 719. So it was clearly still learning, but it just might take you bit more time, a bit more resources in order to do this using a continuous action space. OK, so now here's their robot experiment on the real robot. So they collect a similar data set compared to their discretized environment. So they take half-meter steps, they turn 90 degrees, they just create this sort of data set where they can run their training algorithm on. So they now have taken this room into a grid world, and they evaluate how well it can navigate to two targets. This first one is a door. So here you see, yep, it reaches the door. And then it's going to try to reach the microwave here. You can see at the refrigerator, it's going to take a wrong turn, but then it corrects for that here. And yep, it reaches the microwave. So using their method, they're able to take that policy trained in simulation, train it a bit more in the real world, and it was able to find these two targets using their architecture. And if they had tried to do this with just from scratch, I'm thinking that it probably wouldn't have done as well. So that's it for their contributions and results. So just to recap, they have this new learning architecture, and it generalizes to multiple scenes and targets, and it works with continuous actions, and they were able to transfer this policy to the real world. And here's how it looks like in their simulation. So I can navigate just fine in their simulator. Some feature work that they identified was their simulator actually supports more fine-grained interaction. So it can apply forces to objects, like push chairs away, or it can actually open certain things like fridges or pick up books and things like that. So you can think about this in the real world, where if you have a target you're trying to get to, but there's like a chair in front of you, you're not just going to assume that chair is not movable. You're going to push it away or move it across so that you can walk across that path. Another application for this in the real world is when if you're a robot, you ask your robot to oh, can you check if I have milk in the fridge? Then it would need to open up the fridge in some way. But that adds another action to your environment or to your model, which you'll have to train for. And another situation is that if you're a robot and you enter a room with it's totally dark, then you'd want that robot to turn on the lights rather than just give up because you can't see anything. So those are the sort of areas for future work they identified. It's not clear to me how this model could be extended to incorporate all of this. So I guess it's a big open problem right now to have more sophisticated sort of grasping and manipulation learned in reinforcement learning as well. Wow, that's loud. Good thing I'm done. So thanks. Also thanks to Twitter for all these images, because they're awesome. And just a recap of what we did for questions.